Have you ever stopped to think about how your favorite song, a cat video on the internet, or even the image on your screen right now actually works? It seems impossibly complex, right? But what if I told you it all boils down to just a few surprisingly simple building blocks? Well, today we're going to pull back that curtain and see exactly how it's all put together.
So here's our game plan. First, we're going to look at the signals themselves, the basic ingredients. Then we'll explore the two different worlds they can live in. After that, we'll meet two of the most important signals you'll ever encounter, and finally, we'll see how systems are what put all these pieces to work.
I want you to think about this like a big box of Legos, right? With just a few basic shapes, you can build anything you can imagine, from a simple little house to a giant Millennium Falcon. Well, the world of signals works on that exact same principle. We have a few fundamental signal shapes that, when you combine them in just the right ways, can create any complex signal you can think of. So let's meet them.
Okay, but before we meet our building blocks, we have to get our heads around one really crucial idea. Signals can live in two totally different universes. There's the continuous world, where time just flows smoothly and unbroken, kind of like a river. And then there's the discrete world, where we only look at specific snapshots in time, like taking a series of photographs. And as you're about to see, the rules in these two universes can be totally different. And that has huge consequences for how we deal with everything from audio to video.
In this image, well, it shows the difference perfectly. Over on the left, you've got your continuous sine wave. See how it's a smooth, unbroken curve? It exists at every single infinitesimal moment in time. But then, look to the right. That's a discrete-time sine wave. It's not a curve at all. It's a sequence of individual values. We often draw them with these little lollipops on top, just to really emphasize that they only exist at specific whole number steps in time. It's a totally different beast.
Now, here's where things start to get a little weird and really interesting. In the continuous world, a sine wave is always periodic. You change the frequency, you get a new, unique wave. Simple, right? But in the discrete world, things are stranger. A discrete sine wave is only periodic if its frequency is a nice, rational number. And even crazier, you can have two totally different frequencies that end up producing the exact same sequence of points. This is a massive deal in digital signal processing, something you always have to keep in the back of your mind. All right, so with that key distinction sorted, let's finally meet our first foundational signal. And honestly, it's one of the simplest but most useful ideas in this whole field. Let's call it the perfect on switch.
And this is it, the discrete unit step function. We write it as u of n. And it really couldn't be any simpler. For all of time before 0, its value is just 0, nothing. Then, bam, at time n equals 0, it instantly flips on to 1. And it just stays there, forever. It's the most basic way you can possibly model something turning on and staying on.
All right, next up we've got the unit steps partner in crime. Now this one's a little more abstract, a bit more conceptual, but it is, without a doubt, the most powerful and important signal in all of signal processing. It's time to meet the unit impulse. In the discrete world, the unit impulse, which we call delta of n, is just beautiful in its simplicity. It's a signal that's 0 everywhere, except for one single fleeting moment at time n equals 0, where its value is exactly 1. Think of it like a perfect instantaneous tap, or a single little burst of energy that's there one moment and gone the next.
So what's the connection between our on switch and this tap? Well, it's actually incredibly elegant. Just look at what's happening here. If you take the unit step, u of n, and then you subtract a version of it that's just been delayed by one tiny step, so u of n minus 1, what do you have left? Well, all those ones that go on forever just cancel each other out, except for that very first one, right at n equals 0. The difference between the step and a delayed step is the impulse. It's this beautiful, simple relationship.
And guess what? It works perfectly in reverse too. If we start way back at the beginning of time and just add up all the values of the impulse function as we go, what do we get? Well, it's 0 plus 0 plus 0 until we hit the origin where we add that single value of 1. And from that point on, the sum just stays at 1 forever. We've just built the on switch by accumulating a single tap. It's a perfect duality.
Okay, now when we jump back into the continuous world, our little impulse function gets, well, a little weird. It's not really a function in the way we normally think about them. Mathematicians call it a generalized function. Get this, it has an infinite height, a width of 0, but its total area under the curve is exactly 1. I know, it's a bit of a mind bender, but it's an incredibly useful idea. It represents the derivative of the continuous unit step, the exact infinitesimal moment that switch flips on.
So how on earth do you even begin to visualize something with infinite height and zero width? Well, this slide gives us a great way to think about it. Imagine a rectangle. Let's say its width is delta and its height is 1 over delta. Its area is always going to be 1, right? No matter what delta is. Okay, now, in your mind, just start shrinking that width, delta, closer and closer to 0. To keep that area at 1, the height has to shoot up towards infinity. And the limit of that process, that infinitely tall, infinitely skinny rectangle, that's our guy. That's the continuous unit impulse.
So, we've met our Lego bricks, the sinusoids, the steps, and the impulses. But what are they actually for? Well, they are the inputs to something we call systems. And this, my friends, is where the real magic happens.
At its very core, a system is just a black box. A signal, which we'll call X, goes in, the system does something to it, some kind of transformation, and a new, different signal, which we'll call Y, comes out. That's it. It could be an audio filter taking the hiss out of a recording, an image processor sharpening a blurry photo, or even a complex economic model trying to predict stock prices.
Here is a super simple example just to make this totally concrete. The rule for this system is easy. Whatever input signal x of n you put into it, the output signal y of n will just be 2 times that value. It's basically just an amplifier. It's a very simple system, but it's a real system.
Now, there are a bazillion types of systems out there, but there's a huge, incredibly important class of them that share 2 magic properties. The first one is linearity, which basically just means the system plays fair with scaling and adding. The second is time-invariance, which means the system's behavior doesn't change over time. If you clap your hands in a room today, the echo sounds the same as if you do it tomorrow. And when you have both of these properties together, that's when things get really powerful.
And this brings us to the big reveal, the grand finale. Why did we spend all that time talking about that one single instantaneous tap, the unit impulse? Here's why. If a system has those 2 magic properties, if it's linear and time-invariant, or LTI for short, then you can figure out everything there is to know about it from one single simple test. You just feed it a unit impulse, you see what comes out, and that output, which we call the impulse response, is like the system's complete fingerprint. It lets you predict the system's output for any other input signal you could possibly imagine. It is a truly profound and powerful result.
So, that leaves us with a pretty fascinating thought to chew on. We've just seen how one simple, carefully chosen input, a single tap, can reveal the entire complex nature of a signal processing system. It really makes you wonder, what other simple tests could we use to unlock the secrets of other complex systems in our world? From the human brain to the global economy. What's the unit impulse for understanding those?